We'll now discuss parametric vector form and how to properly represent lines and planes. First, we'll talk about what parametric vector form is, and the best way to do this is through an example. Let's consider a system of equations that we have row reduced, and we get this. We know that since there's not a pivot in every column, that we'll have infinitely many solutions. The first gives me x1 is equal to 3 minus 7x3. The second row gives me that x2 is 5 plus 8x3. And we know that x3 is free. And this is how we've been writing these answers up until now. And now we'll look at parametric vector form. Well, the idea is I'm going to write this as a vector, where I have x1, x2, x3. I know what x1 is, kind of. It is 3 minus 7x3. x2 is 5 plus 8x3, and then x3 is just x3. I'm then going to break this up. I'm going to write the constants, 3, 5, and 0. And then I'm going to do everything with an x3. I get negative 7, 8, and 1. So I can see that now I have this written as a constant vector plus x3 times a vector. And this is parametric vector form. We simply write our solution in terms of a vector and then break it up to where we have a constant vector and then a vector for each free variable. And in general, this is of the form x equal to p plus tv. P is the particular solution. In fact, if we let x3 be equal to 0, we can see that 3, 5, 0 would be the answer. T is our free variable, and then v is the vector that corresponds to this. And this is actually a line. When looking at infinite solutions and parametric vector form, we can usually just consider lines and planes. And how do we know when we have each one? Well, if we only have one free variable, like we did in our last example, this represents a line. If we have two free variables, now we're dealing with a plane. And if you ever have more than two free variables, this is known as a hyperplane. So we'll actually look closer at the cases of a line and a plane and see if we can make sense of them a little bit more. In general, a line can be determined by 2 points. Let's consider the easier of those two cases, where one of those points is the origin. In that case, we have this represented by TV, where v is a vector. If we think about what vectors are geometrically, it can be represented as a point on a plane, and we usually draw this as an arrow going from the origin to that point. All scalar multiples would then give us the entire line through that point. However, what if we want to consider 2 points? Then one of them not the origin. And this is the equation for a general line given two vectors. We have tu plus 1 minus tv. U and v are our vectors, and t is our free variable, our variable for our line. A lot of times we rewrite this as u plus t times u minus v. And this is just a little bit of algebra and rearranging. Let's consider the equation of the line passing through these 2 points. Well, we'll call the first one u and the second one v. Then our equation is u plus t times u minus v. 4 minus negative 5 is 9, and negative 2 minus 1 is negative 3. So here is our equation. And just note that this is one form. If I would have switched these and called the first one v and the second one u, then I would have negative 5, 1 plus t times, now I would have negative 5 minus 4, and 1 minus negative 2. Therefore, these are not unique at all. In fact, these are just 2 points on the line. If I pick any other points and try to do it with those, I would get even more different ways to represent this. Next, let's consider this example. Is 4, 3 on the line represented by 2, -5 plus t, -7, 18? Well, in order to figure this out, we just need to set this equal to the line and try to solve the resulting equation. If I subtract the 2, -5 vector, 4 minus 2 is 2, and 3 minus -5 is 8, equal to t times -17, 18. And now I have two equations. 2 is equal to -7t, which gives me that t is -2/7. And then I also have 8 is equal to 18t, in which case when I divide both sides by 18, I get 4/9. And since t cannot be both of these values at the same time, the answer is no, this point is not on the line. Our next example, well, let's see if these lines intersect. Well, the naive thing to do would be to set them equal and try to solve. However, we have to modify it slightly before we do that. We just need a single point on each of these lines that's the same. That doesn't necessarily mean the values of t need to be the same for each line. Therefore, we need to actually change the variable on one of them and try to solve that. So we'll change the second one to an s. Ideally, now we want our variables on one side and our constants on the other. So we'll do a little rearranging to get t times 3, -25, plus s times -4, -7, 1 is equal to 3 minus 1 is 2, -7 minus 4 is -11, and 9 minus -2 is +11. And now we actually have a system of equations that we need to row reduce. I have 3, -25, -4, -7, 1, and 2, -11, +11 that I now need to row reduce. We'll skip the steps of row reducing this here, but we get 1, 0, 0, 0, 1, 0, and then 2, 1, 0. So we do have a solution. Therefore, they do intersect. In particular, they intersect when this t here is 2, and this one here is 1.